பண்ணி ஆடியோ. Good afternoon, ma'am.
Good afternoon, ma'am.
Good afternoon, ma'am. Am I audible, ma'am?
Good afternoon.
Good
Yeah,
afternoon, ma'am.
Yeah. Sujata, ma'am.
Good afternoon, ma'am.
Good afternoon, ma'am.
sir.
Good afternoon. Good afternoon, ma.
Shall we
Good
start
afternoon,
now?
ma'am. Most welcome, ma'am. Okay, sir. Wait.
Yeah, yes, ma'am.
Sir, we will start within 5 minutes, sir.
Okay, ma'am.
Sir, we will start now, sir.
Okay, ma'am.
Ma'am, shall
Sure.
we start, ma'am?
Yes, ma'am. I'm also joined, ma'am.
Yes.
We'll start.
Good afternoon to everyone. A warm welcome is the first sign of hospitality. It is my pleasure to welcome you all for the fifth and final day of a 5-day national level online PDP on writing research articles in mathematics and statistics. Every morning is a surprise, and every sunrise is a challenge, and each day is a gift. To give the first fruit of the day to the Lord is one of the most valuable ways to show our love to Lord. Prayer is an invocation of the heart. Time spent in prayer refreshes, renews, and strengthens one's life. Let us invoke God's blessings through a prayer song and prayer service. Now, Miss Alina, Miss Priyanka, and Miss Blessy, students from 2nd MSc Mathematics, Auxilium College, will lead us in prayer.
There shall be showers of blessings. This is a promise of love. There will be seasons refreshing, sent from the Savior above. Showers of blessings we need. Mercy drops round us are falling, but for the showers we plead. There shall be showers of blessings, send them upon us, O Lord. Grant to us now our refreshing, come and now honor thy word. Showers of blessings we need. Mercy drops round us are falling, but for the showers we plead.
Prayer. Dear Lord, we come to you this hour asking for your blessings and help as we are gathered together. We want you to come and be in the midst of us. We pray for the guidance in the matters at hand and ask that you could clearly show us how to conduct our work with the spirit of joy and enthusiasm. Come and grant us our heart's desires. Give us the attentive mind that we may concentrate all the time on what we are learning. Let our requests be heard and answered by you, Lord. Amen.
Thank you, girls. To welcome is to show honor and to establish integrity. I now invite Divya E, Assistant Professor from Auxilium College, to introduce and welcome our resource person of the day, Dr. Indra Rajas. Over to Ms. Divya, ma'am.
If we want to reach real peace in this world, we should start educating children, said Mahatma Gandhi. With the great blessing of Almighty God, a fabulous afternoon and a hearty welcome to all. It is my great pleasure and honor to welcome our most respected resource person, Dr. Indra Raja Singh, Adjunct Professor of Mathematics, Savita School of Engineering, Chennai. Ma'am did her schooling in Madurai, BSc and MSc in Bombay University, and MPhil in Madurai Kamaraj University. Her desire for learning did not change. She did her doctoral studies at IIT Madras. Dr. Indra Raja Singh worked at Loyola College for 34 years as the head of the department and 10 years at VIT Chennai. In her long career of 44 years, she has tutored more than 6,000 students who are all well placed across the globe. She guided 25 PhD scholars. She has more than 130 Scopus indexed and SCI indexed journal publications. Ma'am successfully completed 3 funded major DST projects. Dr. Indra Raja Singh organized a series of international conferences from 2007 to 2012 when she headed the Department of Mathematics, Loyola College. She has visited a number of universities in abroad. Madam was a visiting faculty in the University of Newcastle, Australia, and Kuwait University, Kuwait. Dr. Indra Raja Singh is one eminent personality in whom you can find all these qualities. Eminence is not the one-stop destination. Eminence is being that we really need to work hard to uphold. Our mantra is hard work for success. Today, Madam will enlighten us on the topic research problems in graph theory. We are most delighted to have you with us today. Welcome, ma'am. I wish to extend my hearty welcome to all the participants from various colleges and concerns whose presence has lighted brightness to this PDP. And I thank all of you for finding time to be with us today. I once again welcome one and all. Ma'am, we are looking forward to your productive talk. Thank you.
Ma'am, unmute yourself, ma'am. You are in muted now.
Am I audible now?
Yes, ma'am. You are audible, ma'am.
Yes, ma'am.
Thank you.
Yes, ma'am.
Thank you. Good afternoon, everyone. I thank Dr. Sujata and all the organizers for having given me this opportunity to be with you all today. So let me begin with my presentation. I shall share the screen now.
Yes, ma'am.
Is it visible?
Yes, ma'am. It is visible, ma'am.
Okay. All right. Today, I thought I would discuss a few research problems in graph theory. So all of us know what a graph is. It's a network where we specify relationships among a collection of items. We have the nodes or vertices and edges joining pairs of vertices. So what we get is called a graph. And two nodes are neighbors if they are connected by an edge. So this is only a basic structure of a graph where we have the vertices and the edges. These graph models impact graphic network design, drug research, computer chip design, arranged marriages, scheduled fights and exams, architectural floor planning, designing social networks, for example, Facebook, job assignment, designing electrical networks, facility locations, Google Map, optical fiber communication, etc., etc. In other words, these graphs in day-to-day life, they depict mathematical models so that we can solve problems based on these models. So graph theory is nothing but a tool which is used in communication networks, power transmission systems, transportation networks, and computer architectures. So to begin with, let us see some of the networks. What is a communication network? The vertices represent mobile towers, edges represent signals and communication links. So this is called a communication network. So what are vertices and edges here? They are the mobile towers and the communication links. When it comes to transportation network, vertices represent bus stops, stations, etc. Edges represent roads, railway tracks, etc. When it comes to a social network, in a social network, the vertices are human beings. So vertices represent people, edges represent relationship between them. So here is Facebook, where there are 2.936 billion active users in April 2022. In other words, it is a giant graph where so many vertices are present. And we also have, apart from Facebook, we have Twitter, Instagram, etc. There are many other social networks. Look at a Google Map. This is something which we use almost every day in our life. Suppose I want to travel from one place to the other. I look at the Google Map so that I will know the shortest route which takes me from my destination from my place to my destination. So you look at the Google Map as a giant graph where vertices represent the what you call towns or the area where you live in, and the lines represent railway tracks, bus routes, air routes. So everything is represented in the Google Map. And then sometimes it also gives you an alternate route if the shortest route is congested. Here in the Google Map, we use shortest path problem for which we have algorithm. All right. So this Google Map is considered to be a giant map, but when we look at a particular area, it is just a small subgraph of the given graph. What are chemical graphs? Chemical graphs, vertices represent atoms and edges represent the bond between the atoms. So finally, when we draw the compound, chemical compound, the graph that we get is a chemical graph or a molecular graph. For example, the calcium fluoride, we have this particular structure. A diamond crystal. You look at the right hand side, the carbon atoms, they are placed in this particular manner, and this structure represents a diamond crystal. NaCl. What is NaCl? The common salt that we use in our houses every day. Even that has a graph structure. Na and Cl take up the atoms, the position of the vertices, and the bond between them is represented by edges. What is a biological network? We have the human brain is there, and we have a hub from where we pass on information or instruction to other parts of the body. So through nerves, the impulse is being carried from the hub to the other parts of the body, and therefore the entire human body is considered to be a graph which takes instruction from one place to the other. Other biological networks are the chemical structures are the vertices, and the physical communication links are the blood vessels and the nerves. Now we come to computer networks. See, we have seen transportation network, we have seen chemical networks, we have seen social networks. So what is the difference in all these? Basically, all of them are graphs. All of them are graphs which are addressed as networks. Here again, we have a computer network where basically we have only a graph. The vertices represent processors and the lines between them represent the communication link between the processors. Standard networks, we have path, cycle, mesh, hypercube, circulant. Let's see some of them. This is called a hypercube network. Here, suppose we take the third diagram where we have 8 vertices. What is the meaning of this? We have 8 processors placed in the respective corners, and lines between them represent the communication links. Now, we can also understand it this way. Suppose I'm given 8 processors, I can put it in a circle. So that is called a cycle. I can put it as a path, starting from one vertex to ending with the 8th vertex. So what is the difference among all this? The difference is the way they are interconnected. That is why when the interconnection changes, we get different interconnection networks. These are all standard networks because they are used in the industry today. What is the butterfly network? What I have drawn here is the butterfly network. This butterfly network is used in IBM, etc. Now, here again, I want you to note that the way they are connected differs from hypercube. So hypercube, see, the processes are all the same. The vertices are all the same. Only thing is the way they are connected, they are named differently. So hypercube is different from butterfly network. It is different from Bennis network. Bennis network is nothing but back-to-back butterfly network. So these are all some of the standard computer networks. Circular network, where the vertices are 0, 1, etc. up to 11. And these networks are mainly used in telecommunication networks. Because, see, when you imagine a huge area where the towers are to be placed, we will exactly locate where the towers are to be placed and how the communication links are to be given. This is carbon nanotube. Nowadays, smaller and smaller processors are brought into the market are being used by us. And for that, for the processor, instead of using a big network, we can go for nanotubes. So the most famous ones are the carbon nanotubes. Boron nanotubes are there. They all have, look at the structure there. The dots represent processors and the lines represent the communication links between the processors. So finally, what you are looking at is nothing but a graph. So as a graph theorist, whether you are in the computer science or in chemical networks or the chem informatics or bioinformatics, where biology is combined with computer science, wherever I am, I find that all these basic structures, they have different names, but for me, they are all graphs. Standard networks at board designs. See, you know the computer chip. All of us have seen the computer chip. You'll find that you have certain butts placed over there. They are the processors, and you have the lines placed between processors. They are the communication links. When you look at it, have used only sweeping curves, but this does not mean that you can draw it any way you want. Probably this should be isomorphic to hypercube, or maybe it is it is isomorphic to butterfly, so that you have standard networks on the computer chips. So all these computer chips that we are using, so when I say this is being used in IBM, hypercube is being used in IBM, that means IBM uses hypercube network to be placed in the computer chip. So they appear like this, even though only the sweeping curves are there. When you redraw the whole thing, they will appear like a hypercube or a butterfly or a circulant or a hypertree. There are plenty of standard interconnection networks. They may represent one of them. So it makes it meaningful for us to study the networks to be placed on the computer chips. All right. So far we have seen networks, different types of networks. All of us now realize that any network is a graph. Depending on the problem, depending on the situation, the vertices will represent railway stations, vertices will represent human beings, vertices will represent atoms, vertices will represent computer processes. Okay, so depending on the problems that we face day-to-day life, in day-to-day life, we model the graph in such a way that the problems that we face can be solved in the network. So far we have seen a number of networks, and now we are going to see some of the problems that can be done on worked on these networks. And I have chosen locating domination, burning and firefighting, acyclic coloring, and transmission in graphs. These are the problems that we are going to discuss. Okay, if it's going to be a long session, at the end of each problem, we can have some discussion. All right, let us start with locating domination. So domination and locating domination in graphs. What is a dominating set in a graph? A subset S of vertices is said to be a dominating set if its neighbor means all those which are adjacent to the vertices in that particular set. Yes, all those together should constitute the whole vertex set. Now look at the graph G given over here. I have marked 2 and 5 in red color. So let us take S to be equal to 2, 5. Is it a dominating set? That is a question. So let us look at the neighbors which are adjacent to 2 and 5. You find that 1 is adjacent to 2 as well as 5. So no problem. 4 is again adjacent to 2 and 5. Again 4 is there. And 3 is adjacent to 2. That means every vertex which is not there in S is adjacent to some vertex in S. So this S is called a dominating set. Let us take one more example. Let us take this particular graph. There are 4 vertices marked in red. If you take those 4 vertices, look at the neighbors of all these vertices, you will find that no vertex of the graph is left out. Every vertex, for example, V4 is adjacent to V2, V1 is adjacent to V2, V3 is adjacent to V2, V5 is adjacent to V6, V7 is also adjacent to V6. So it goes on like that. We find that all those which are not in D1, they are all adjacent to some member of D1. Therefore, what is our conclusion here? D1 is a dominating set. Look at this one. The number has increased now, V1, V3, V6, V8, and V10. Again, I find that the condition is satisfied. Every member outside D2 is adjacent to some member in D2. Now let's look at here, this one, D3. So D3 is V4, V7, and V10. So here there are only 3 vertices. Again, you find every member which is not in D3 is adjacent to some member in D3. Therefore, D3 is a dominating set. What is the meaning of minimum dominating set? That means you cannot reduce this number from 3 to 2. 3 is the minimum number of vertices required to dominate the graph G. The D is called the domination number. All right. So this is usually represented as gamma of G. All right. What is application? See, look at the word marked in red, monitoring. So when every vertex is adjacent to some vertex in this particular set, in this monitoring set, that means this small set of minimum number of vertices can monitor the entire graph. All right. See, they are useful in communication networks, electrical networks, land surveying, and many more. Because monitoring comes when you want to check whether all the neighbors are functioning properly. So domination helps you in monitoring all the vertices in the given graph. That is why this monitoring, this domination problem has gained a lot of importance. And in mathematically, it is called an NP complete problem. NP complete means non-deterministic polynomial time. What is the meaning of that? If you start solving this for an arbitrary graph on 100 vertices or 200 vertices, in polynomial time, you will not be able to find the answer. So if you are not able to find the answer in polynomial time, how will the industry depend on you? We mathematicians, we know that unless we give a solution that cannot be made use of in computer science or in any other area. So how are you going to help them? You are going to say, see, so many members of the given graph will monitor the entire system. All right. So if that is not achieved in polynomial time, then the industry will not rely on you. So, but mathematically, we prove that these are all NP complete problems, and therefore we go for standard networks. So in the beginning, I spoke about a lot of standard networks. Why we are studying these standard networks? Can I solve the domination problem in these standard networks? You will be surprised. Even in standard networks, it is not that easy to find the domination number. Even for hypercubes, only up to a certain level they have solved. Beyond that, they have not solved. So it still remains an open problem. Therefore, why we stick to standard networks? This is the reason. Now let us come to locating dominating set. All of us know what is meant by a dominating set. Now we add one more condition to locating domination. What is that? You take the vertex set of the graph G. S is a dominating set. Okay, we choose S to be the dominating set. Now, if I take a pair of vertices outside S, I will look at the neighbors of U and V in S. Outside, I don't bother. But in S, what are all the vertices which are neighbors to U and V? If that set is the same for both U and V, in other words, the neighbor of U and the neighbor of V intersection in S, if it is the same set, then it is not a locating dominating set. They should be different for every pair of vertices. Look at this particular one, U and V. U has 5 black dots and a blue dot outside. V has 5 black dots and a green dot outside. What is the meaning of that? The intersection of the neighborhoods, they are not the same. U has blue outside, V has green outside. Therefore, this is true for, remember, the definition is like this, for every pair of vertices. So for both U and V, I have shown in this diagram. For every other pair also, this should happen, in which case we say that S is a locating dominating set. Okay, so with the help of this locating dominating set, what is that we are going to achieve? All right, let us go to uh, why do we need an LDS? Okay, the monitoring system, if there is an intruder or a fire, or a intruder means it can be a thief. If he is visiting a particular place to for burglary, the alarm will send a signal. Okay, so if there is a if it is a if the alarms are placed at the dominating set, then definitely they will send an alarm. But let us see what is the difficulty that we will be facing. We'll be facing if we have the dominating step alone. All right. So first, let us understand that there are two steps. One is the dominating set step, and the other is the locating dominating step. All right. Let's see what it is. Let us look at this particular situation, a real life situation where there are 6 houses. Okay, there are house number 1, 2, 3, 4, 5, and 6. Okay, now I place sensors at 3 and 4. Let's see why I do that. Look at the right hand side. I redraw what is given on the left hand side as a graph. What is that I have done? I have taken all the sensors the 6 houses as vertices. Okay, vertex number 1, 2, 3, 4, 5, and 6. Okay, and then I join two vertices if there is a common wall between the two. Let us take 3, house number 3. Between 3 and 5, please look at the left hand side. Between house number 3 and 5, there is a wall. So between 3 and 5, there is an edge. Between 3 and 4, there is a wall. So between 3 and 4, there is an edge. Between 3 and 1, there is a wall. Therefore, there is an edge between 3 and 1. This I do for all the other houses. And finally, what I get is the graph that I get on the right hand side. Now, for the graph on the right hand side, you notice that 3 and 4 forms a dominating set. In other words, in the dominating set. Okay. So I now decide to place my alarm in house number 3 and house number 4. All right. Now, here is a burglar. He is visiting. Here is a burglar, and suddenly the alarm in house number 4 sounds, gives a signal. House number 4 gives a signal. All right, so you are elsewhere monitoring the system. You hear the signal, you see the signal, but then you do not know in which house the burglar is. House number 6. If you are going to run to both the houses, it's a waste of time. He may escape. So now I have to decide. Dominating set alone will not help me. So I have to see that the sensor or the alarm has to be placed in more than 2 places. So what is that? The locating domination helps. Let us look at the same diagram, the same situation where I have the graph on the right hand side. Now I have taken 1, 3, and 4. This is the locating dominating set. Let us see why it is locating dominating set. Let us go to the previous one and see. You find that you have the vertex 4 has 2 and 6 have 4 as the neighbor. That is why we are having a problem. All right. So this should be avoided. So what we do is we see that the neighbors are all distinct. Now let us look at vertex number 2. Vertex number 2 is adjacent to 1 and 4. What are 1 and 4? They are in the LDS. All right. So these are the members of the dominating set. So 1 and 4, 2 is adjacent to 1 and 4. 6 is adjacent to 4. 5 is adjacent to 3. So I find that those which are outside are all adjacent to vertices in the locating dominating set, but all the neighbors are distinct. All right. All the neighbors are distinct. 3, 4, 1, 4, they are all distinct. Now look at the burglar. Suppose he visits house number 6. What is set off? Which alarm is set off? House number 4, the burglar alarm is set up, and we are able to find out exactly the location where the burglar is. Now, when he goes to house number 2, you find both 4 and 1 signals. So I'm again able to uniquely locate that burglar is in house number 2. So 4 and 1 together give me the location of burglar. I don't have to locate that locating. You find out where the problem is, that is domination, and then you locate where it is, that is the locating domination problem. All right. So you find this is a very simple example. But now, if you work on this problem, for different architectures, I won't guarantee that you will get the minimum dominating number, locating dominating number, but definitely very challenging problem. Any network you think of, probably your hypercube, your trees, you can go for other architectures, butterflies, banners. Try to find out that particular network and try to find out you're able to prove that that number is minimum. Definitely your problem will get accepted. The reason is it is a NP complete problem first of all, and you are working on networks which are being used in the industry today. Solutions from you mathematicians, and therefore if you are able to solve this problem for various architectures, you will get them published. So before then what else do I have? Okay. So before I pass on to the next problem, I would like to tell you how to write a paper on this. All right. So all of us know there is a problem called locating domination. All right. This can be used in multiprocessor architecture. It can be used anywhere in the electrical network where if some neighbor that grid or whatever immediately identify that something has gone wrong. That is the first step. The second step is the location, where exactly the current is gone. Okay, so you have to find out exact location. So we know that this problem is there, and there is a definition which helps you to solve this problem. And mathematically, it has been proved that it is an NP complete problem. Now, what is that we are going to do? Suppose I feel that I should take up some architecture and I start working on it. I get a result, and sometimes it has happened to me many times. We send it to some journal and we get back this one comment saying part of it has been already worked, somebody has worked on it. These are all some of the results already known. A lot of honesty, you would have worked on that particular problem. You would have enjoyed doing that particular problem. So you would have noted down all the results. You would have written it neatly. But then when you send it to the journal, you realize that somebody else also has worked on it, because when there are published papers, it is thrown open to the entire world. Everybody in the world who is interested in domination will also read locating domination, and therefore people will start working on standard networks. Okay, so what will happen is somebody might also find out the same result and get it published. So it will be a big disappointment for us. So what is our first step? So I spoke about the last step, but what is your first step? The first step is the moment you realize that you like a particular definition, you feel that you can work on it, you feel that you like working on that particular definition and the standard architectures that you choose. What is that we have to do? Immediately go for literature survey. It is a must to do literature survey. Look for all the keywords that you can think of: locating domination, different types of networks. Okay, so whatever keyword you can think of. See, if you want more keywords, what you should do is look for the base paper. Somebody would have published some paper on locating domination. For example, Slater has done it. Slater has published a beautiful paper on that. Take that particular paper. Okay, start looking for keywords from there. Use those keywords, and nowadays everything is available with you. Google search is there. You just put the word keyword, immediately you get the result. Okay, so immediately you will know who all have worked on it. Note down everything. So that literature survey, sometimes if the problem is new, it may not be too long. But sometimes if it is a very old problem, a lot of literature survey will be available. It is very good for you to mention these in the introduction. So that shows the strength of your paper. That shows that you have done a lot of literature survey. You have noted down a lot of things which have been done on that particular area. So the new paper that you write, if you write a beautiful introduction with all that is available, don't make it too long, but make it long enough to make the referee understand that you have understood the subject thoroughly. If you do that, you will also have the satisfaction of doing something new, And those referees who go through your paper will also be happy to know that you have gone through all the literature survey. Look for literature survey, look for papers published in 2022. Don't leave them out. All right. Nowadays, it is very easy to find out. So 2022 papers, that is the first thing that you should realize when you write a journal article. The second one is when I say you look for journal articles which are already published, don't go for any ordinary journal. All right. Go for uh, journals with very high impact factor where papers on this topic are published. Take one or two of those papers. Don't go for very ordinary journals. Please do not do that. Go for very good journals with high impact factor. Check that first. Who are the authors? When was the result published? In which journal was it published? Okay, is it very recent? If it is 2021 also, you should not be satisfied because we are almost in the fag end of 2022. So even that you should check. One by one, you should note down and see that what you are doing is something different from what others have already tackled. This is the key thing that you have to do in any research article that you are preparing. Once you do that, definitely your papers will get accepted. All right, so this is the literature survey. If you have any questions, you can ask me now. Shall I proceed now?
Yes, ma'am. You can proceed, ma'am.
Okay. So the next problem I thought I would discuss is burning number problem. What is the meaning of burning? You are going to burn the vertices. Okay, a graph is given to you and you can burn the vertices. What is the meaning of burning? Probably you have a network. Network means graph. You have some information at one particular vertex, some data you have. You want to pass on that information to every other vertex in the network. You can also take it as COVID outbreak or some outbreak of disease. At one particular area, you have some disease. It is infectious. So what happens is you would like to know how far it is going to, how fast it is going to spread so that the entire area is going to be affected. So these are some of the basic things that we usually think of, but not as a mathematical model. So if you want to have it as a mathematical model, have the entire area as a network. Okay, so all the places that you can think of, they are all the vertices, and then you have the communication links between them. Now the data has at one particular place has to be passed on to every other place. We may use different protocols. What is the meaning of protocol? Rule. Different rules are there. One such rule is called burning number problem. The rule is this. What happens is, you see, in the beginning, every vertex in the network is not burnt. There is no fire anywhere, no burnt vertex. All right. Now, there are two ways of looking at this. One is, what you do is the first step. In the first step, I'll show you. In the first step, what you do is you burn all the neighbors of the already burnt vertices and choose a new vertex which is to be burnt. Shall I repeat? Burn all the neighbors of already chosen vertices and see the word and burn a new vertex. It could be thought of the other way also. Both give you the same result. All right. So let us see what happens now. All right. In the second step, what will happen is already burnt vertices will burn their neighbors, and then you will choose a new burnt vertex. Not burnt vertex, a vertex to be burnt. New vertex which will burn. So finally, you will burn all the vertices in the graph. All right. In how many number of steps? Minimum number of steps. You burn all the vertices in the graph is called the burning number. All right. So in shortest duration of time, data will be passed on from one vertex to all the other vertices in the network. All right. The burning number is the minimum number of rounds. Let us take the first illustration here. Here is some arbitrary graph. All right. So what we do is initially, before you go into this, initially there are no burnt vertices. So no neighbors to be burnt. So you choose a new neighbor X1, which is going to be burning. So X1 is burnt in step 1. In step 2, what are you going to do? You are going to choose new vertex and burn all the burnt vertex, neighbors of the burnt vertex. So in step 2, you are burning all the neighbors of the already burnt vertices. All right. Now this is over. Now what should I do? I go to the step 3. Step 3, I choose one more vertex, X3, and now I check whether all the neighbors are burnt. So I do it one by one. I find that all the neighbor, in other words, all the vertices in the graph are burnt. Now, what is the meaning? In 3 steps, I have burnt all the vertices. What is a mathematician's question? Mathematician should ask, can I burn it in less number of vertices, with less number of vertices? That is the problem. See, burning number problem is also incomplete. And therefore, given a standard network, how information is diffused from one to the rest using a certain protocol is not easy. So this is one protocol that we have used. Let us look at the KN. What is KN? Complete graph on n vertices. So I start burning now. One vertex is burned. In the next step, I choose another burning vertex and all the neighbors of the already burning vertices. So I find that in 2 steps, I am able to burn all the vertices of KN. All right. So this is my so the burning number of click is equal to 2. Let us take a path. I burn V3. Then I burn V7 and all the neighbors of V3 in the second step. I burn V9 and all the neighbors of the already burnt vertices. That is the third step. So I find that the number is 3. Again, the problem is, can I reduce? Okay, Donato was the first person to introduce this burning number problem in the year 2014. And in that paper, he has already proved that the burning number of Pn is equal to roof of square root of n. It is not very difficult, but then this has been already worked out. He has done it for path. We can do it for mesh. I'll show you mesh also. Let us look at mesh. Here is a vertex which is burning. Next one, another vertex and all the neighbors. Another vertex and all the neighbors. The circled ones are the chosen vertices. And finally, I find that all the vertices in the grid are burning. How many vertices have I chosen? How many steps have we chosen? We have chosen 4 steps here. All right. So the burning number in this case is 4. But unfortunately, fortunately or unfortunately, this problem has not been solved for a general grid, not even for a square grid. Okay, here is a small example, 5 cross 5. We are able to give the answer. But if it is 100 cross 100, what shall we do? How do we find the burning number? The problem
So, dear participants, there is a small technical issue. We'll get back to you soon.
That is 55 in a few minutes.
Am I audible now?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am, you are audible.
I'm sorry, current went off. I had to get it done again.
No problem, ma'am.
Okay, thank you. Testing. Is the screen visible?
Yes, ma'am.
Okay, I'll proceed.
Yes, ma'am.
Okay, 1 minute. Okay, I'll now proceed. I think I stopped with this grid. Am I right?
Yes, madam. Yes,
So
ma'am.
I'll pass on to the next one. K burning number. This concept was introduced in the year 2022 by our research group, where a group of vertices were allowed to burn at every instance. So you find here on the right and left hand side, it is just the burning number where T1 represents the first vertex to be chosen, T2 the next one, T3 the next, and T4 the next one. So the burning number in this case is equal to 4. Whereas on the right hand side, there are two vertices marked in red. Both are T1. All right. So at time T1, both the vertices are chosen. They are burning. And in the next instance, T2, there are two blue vertices, one at the top, one at the bottom. Both of them are burned along with all the neighbors of T1, T1. All right. This happens and this gets over in 3 units of time. So you find that the number of the time is reduced when you choose more number of vertices. All right. This paper, this problem has already been accepted in a journal, in a very good journal. And the open problem is you find that Bonato has proved that for Pn, it is root n, And we have proved that dk of Pn is root of n by k. So similar relationship between burning number and k burning number, you can try for other architectures like, again, hypercubes, mesh, and several other architectures are there. You can take any one of them and you can start working on that. All right, so this is about the k burning number. This is the literature survey on burning number. Anthony Benotto, in the year 2014, he introduced this particular problem. He had visited VIT in the year 2016, and in our conference, he discussed this burning number problem. So from that, we took off, and for nearly 2 years, we didn't work on that particular problem. Then after that, we started working on that, and at present, we are working on k burning number. And there is one more that is called edge burning number. So you can think of edge burning number, k burning number. These are all variations of the burning number problem. So there are several research gaps. So you find that you can have a number of research problems which can be taken up from burning number. Similar to burning number, there is one more problem which is very, very interesting. Okay, this is a problem you can do for the same thing I have shown, to show that you can start working on burning number of butterfly network. You can start working on burning number of Venice network, on circular networks, and you have hundreds of such networks, not three. I have just shown here. There are hundreds of standard networks, so you can work on burning number of these networks. All right. This is another example, another problem, firefighter problem. This again was introduced prior to burning number problem. Again, Benotto has got a number of papers on firefighter. Let's see how it works. At every stage, the vertex in a particular graph is either burnt, or it is saved, or it is available. Let's understand what it means. Fire starts at a particular vertex, and in time steps, it goes, it starts burning all the neighbors. So let's take the first one. This is a nice example where the fire starts at the central vertex. All right. Now, immediately, one firefighter appears there and does not allow the fire to spread to the two of his neighbors which are behind him. So he stops the fire there, and therefore, let us use the word that vertex where the fighter is, that is already saved. And there are two more at his back. They are also saved. They are available, but they are already saved. So 3 vertices are saved in this step. Next is all the neighbors burn. Immediately one firefighter appears, but he is not able to save much. So again, we go for all the neighbors to be burnt, and we find here that only the 2 vertices which are used by the firefighters and the 2 saved ones, they are all the saved ones. Now let us see what the problem is. See, it is very nice to see how it works, but what is the problem here? You have to save maximum number of vertices. Okay, what was burning number problem for you? In the burning number, you found minimum time so that the entire data is given to all the vertices in the network. That is minimum. Here what happens is the firefighter fights. He saves, and he also has all the neighbors saved. So you find that you have to find the maximum number of vertices to be saved, and that is your problem here. All right, that is the problem. Now, what is S and GV? Maximum number of saved vertices in G if a fire starts at V. So where the fire starts, even that is important. Let us see how it goes. Let us take the path here. Now, the result is given over there. If V is an end vertex, the answer is n minus 1. What is the meaning of n minus 1? N, all the other vertices will be saved. But else means what? V is not an end vertex, then only n minus 2 vertices can be saved. Let us see. Suppose you have it in the middle, not middle, interior vertex. What happens is, In the next step, a firefighter appears and he saves 3 more vertices on the left hand side. So the firefighter vertex is there, 3 more vertices on the left hand side. So 4 of them are saved now. But the next neighbor is not, we are not able to save. So the neighbor of the vertex which is burning, that is also burning now. Now bring the next firefighter in. Now you find that the 2 vertices on the right hand side are also saved. So you find that 3 plus 2 plus 2 more vertices where the firefighters are. So you find that 5 plus 2, 7 vertices are saved, which is nothing but 9 minus 2, n minus 2. Now you can always imagine if you place that firefighter at the end, the very next one will be a firefighter saving all the other vertices on the other side. So you find that this result is true. These are all appearing in the published papers, but already they have already solved for certain easy architectures. I advise you to go for other architectures. That is why the literature survey is very important. Okay, KNB, it is just, KN means complete graph, it's 1. And if it is a hypercube, the answer is n. These are all already obtained. Let us look at Cartesian grid, P7 cross P7. Now, look at the fire burning over here. Immediately, there is a firefighter who will solve all the 4 vertices on the same row on the right hand side. Okay, so that is one. See, this is how you decide. 4 are saved. Now, what happens? All the neighbors are burnt. So, another firefighter appears. He also saves 4 vertices on the right hand side. So, he keeps, so all the neighbors burn, another firefighter appears. Neighbors burn, another firefighter. Neighbors burn, another firefighter. Neighbors burn, another firefighter. Again, neighbors burn, another firefighter. Now tell me, will the fire spread to all the vertices, to those vertices on the right hand side, those which are not burning? See, like a wall, all these firefighters are there. So on the right hand side, whatever you have, they will not burn. All right. So you find that these are all the vertices which are saved. Okay, maximum number we have to save. Now the question is, for a grid, is this the maximum number, or is there any other way of looking at burning this vertex? Let us look at the next one. Let us start burning at the end. And that's why I said the place where you start is important. See, you have the fire burning there. The firefighter appears there. He has saved 5 vertices on the right hand side. Next one, again the firefighter. So keep doing it. So what happens is, at one stage, you cannot go any further. And therefore, now look at all the vertices which are saved. Except for the vertices in the first column, all the others are saved. Therefore, I find that this is a better result than the previous one. So this tells me, as a mathematician, can I reduce this number further? That is what I'm looking for. So when I can I increase the saved vertices more? If I'm able to do that, then what is the optimal value? How many vertices can be saved? For grid, it has already been proved, but then there are hundreds of other architectures where the result has not been obtained. So again, you can go for such problems. Okay, so this is the second problem that I discussed. Now I go for I hope listening will be very tiresome. Let's see. Let's go to the next one. Acyclic edge coloring. Many of you will be working on coloring problem. All right, edge coloring problem, vertex coloring problem. Here is something different from that. It is acyclic edge coloring. So we shall first begin with what is meant by a coloring problem. What is coloring? Coloring means vertex coloring. Color the vertices in such a way that adjacent vertices do not receive the same color. Look at the graph which is given over there. How many vertices are there? 6 vertices are there, and we have given 6 different colors. Is it a valid coloring? Yes, obviously adjacent vertices will not receive the same color. But will this be the coloring problem? What is the problem? Always remember, problem will be optimization. Either you may have to maximize or you may have to minimize. The previous example was a good one. For burning number, minimizing. For firefighter, maximizing the saved vertices. Okay, so here again, when you have the coloring, if you have 100 vertices in a graph, you can use 100 different colors. Problem is solved. Adjacent vertices will not receive the same color. But what is the problem here? I cannot use 100 colors. I have to bring it down. So to show that, I will give you an example, which many of you know that particular example. But anyway, look at this particular one. In the left hand side, you have 5 different colors. Then we have used 3 colors. So the question is, can I reduce it further? When I come to the one which is down, you find that there is a conflict. Why is the conflict? The 2 red colors are adjacent, which is not allowed. So it is called a conflict. All right. So these are all applicable in scheduling, radio frequency assignment, register allocation. There are several more applications to this. All right. Now, as I told you, why this minimum number of colors is necessary, I'll give you show you by an example. All right. Look at that which is in the yellow. Cannot be offered at the same time. What is the meaning of that? Maths and biology cannot be offered to a set of students at the same time. What should be the reason? From that set, at least there will be one student who has opted for mathematics. Here, we would have also opted for biology. If he is opting for both, we cannot have mathematics and biology in the same period. All right, scheduling. How are you going to schedule? If there are 100 subjects, are you going to have 100 hours? No, you have to find out which are all free slots. Okay, where students don't clash, there is no conflict. That is what we are going to see. So look at the right hand side. Maths and bio, there is a conflict. Maths and chemistry, there is a conflict. Bio and music, there is a conflict. What is the meaning? There are students who have opted for biology. They have also opted for music. There are students who have opted for art. They have also opted for economics. So they are all listed out here. So how are you going to solve this particular problem? That is, what is the problem here? The scheduling. How are you going to schedule these classes in minimum number of periods? Okay, so what you do is you take all the subjects as vertices. Mathematics, chemistry, art, etc. Take them as vertices. Now let us see, look at the conflict. Maths and biology, there is a conflict, so draw a line. So keep doing it for all the subjects. What I get is a conflict graph where, remember, mathematics and chemistry should be separated. Why should they be separated? They cannot be offered at the same time. They have a line between the two. So what I do is I give a coloring for it, proper coloring for it. Maths I will give red, chemistry I will give blue. What is the meaning? Blue will go into one slot, red will go into another slot. That means there won't be any clash. So wherever there is a clash, you give the coloring, see that the conflict does not arise. So here you find that there are 3 colors, minimum 3 colors are required to color the vertices of the graph so that there is no conflict. So what was with some 8 or 9 subjects, instead of having 9 hours for all the 9 subjects, what you have done here, sorry, there are 6 subjects. Instead of having 6 subjects, you now have only 3 periods. In 3 periods, all the 6 subjects can be covered. This is scheduling. The same thing can be used for this airplane scheduling, train scheduling, examination scheduling. So all these are covered under coloring problem. All right. So what is meant by edge coloring? So the same thing carried over to edge. Take a vertex, take all the vertices incident at that particular vertex. All the edges should receive different colors. In other words, if you take all the edges incident at a particular vertex, they should get different colors, but then that is not the problem. What is the problem? The problem is to minimize the number of colors. To minimize the number of colors. And that minimum number is called chromatic index. The previous one is for vertices, that is called chromatic number. So chromatic number is for vertices, chromatic index is for edges. All right. So these are some of the applications for edge coloring. And now I'm going to go for acyclic edge coloring. What is meant by cyclic? Cyclic means there is a cycle. Acyclic means there is no cycle at all. So what is that which determines that word acyclic? Look at the four cycle which is drawn there. I color them with red opposite sides, blue opposite sides. What is that I get? I get a proper coloring. This is also minimum. It cannot be reduced any further. But you find that there is a cycle which is formed of two colors. Let me read it out. 1, 2, 1, 2 is a cycle colored with two colors, which is not permitted. So read the second line. There is no two colored cycle. So this is not permitted in this particular acyclic coloring number. All right, let us look at the same problem. You find that 1, 2, 1, 3. Cycle is there, but how many colors are used? The three colors are made use of. Therefore, you find that this is acyclic edge coloring. What is acyclic edge coloring? That which is on the right hand side is acyclic edge coloring. All right. So the same thing is given here. So you find, okay, the point to be noted here is union of any two color classes induces a path, set of paths. Why? Can you answer me? Union of any two colors cannot give a cycle. That is why we have said acyclic. Union of two colors cannot give you a cycle because you have banned it. You have said that two colors cannot be given to a cycle. Therefore, if at all you take union of two colors, they should give only a set of paths. This is the crucial step in the discussion of this particular problem. Shall I repeat? Using two colors, you cannot have a cycle. So, two colors cannot induce a cycle. So, if at all you use two colors, they should give you only a set of paths. Okay, so that is the crucial step here. Let us move forward. Finding the minimum number is the acyclic chromatic index of a graph. That is the problem. It is true, proved to be NP complete. Please remember that all the problems that I have discussed so far are all NP complete problems. All right. Now look at what is this conflict. There is a cycle blue, red, blue, red. So this is not acyclic edge coloring. Whereas when you look at the valid coloring, you find that there is no cycle used using only two colors. Using only two colors, there is no cycle there. So that is a valid coloring. But what is your problem now? The problem is to find the minimum number of colors used for acyclic coloring. Okay, what is, we immediately jump to applications. What is optical fiber? Optical fiber means, look at this one. These are thin strands of glass. These are called optical fibers. Why is it called this is used for communication, optical fiber communication. Why is it used? The reason is you can send message across oceans. See, now communication links are wires, means you have to lay the wires. But now here what happens is at one end across the ocean, in one continent you have one vertex, in another continent you have another vertex. So you can send message across the ocean. All these cables will be laid below the ocean level, and there are switches to pass on the message from one to the other optically. Light energy is used. And finally, when you receive the data at the other end, that can be converted into mechanical energy. So this is the optical fiber communication. For that, we make use of the wire length problem. All right. So what is this wire length assignment problem? Now, when you bundle the whole thing in your cables, different strands will be there in one particular cable. So you cannot use the same frequency to send data from one point to the other when they are all bundled up there. All right. So when there is a clash, when there is a conflict, I will decide that I will not use the same frequency. Let us see when the clash arises. Look at, it's a very simple graph that you are going to take. 1, 2, 3, 4 paths induced by two color class. Okay, I have used four colors here. I have not used minimum color. 1, 2, 3, and 4. Now you find 1, 2 induces a path blue. 1, 3 induces the green and the violet one. Then you have 2, 3, 2, 4, 2 color classes induce only paths. Next, what I do is I take all this, I take the paths as vertices, and when will the conflict arise? When two paths cross the same edge. For example, this blue and this green. All right. These two cross the same edge marked 1, and therefore there is a conflict. So between P1 and P2, P1 is path marked red, blue, green is marked green. So between these two, there is a line. There is a conflict. I cannot use the same frequency. So what I do is I keep doing it. Now look at this one, 1 and 4 induce red one. So between blue and red, there is a edge. Between green and red, there is an edge. So I keep doing it so that this conflict graph is completed. And then what I do is I find the chromatic number for this conflict graph. This is my 3. And my theory says this is the minimum number of frequencies to be used to send a message across oceans, across mountains, across any terrain. Okay, so to use optical fiber communication network, one has to study what is a chromatic number, what is edge chromatic number, and what is acyclic chromatic number. This is the flow chart which is shown here. And now the next question is, as I told you in the beginning, the square, the 4 cycle that I choose, I gave 4 different colors, 1, 2, 1, 3, and 4. So the chromatic number was 3. Now what I do is, using acyclic chromatic number, I have 1, 2, 1, 3 is a cycle which is using 3 colors. I do the same thing with 2 color classes. I draw the conflict graph. Now the chromatic number has become 2. Okay, see the beauty of it. If I use any at randomly, I use chromatic number, I get 3. But if I use acyclic chromatic number, I get the answer as 2. So 2 frequencies are sufficient for me if my layout is a 4 cycle. This has not been worked out for many of the architectures. This is a very simple example. Even for mesh, there is no answer. So I request that if you are really interested, you should go ahead with such architectures. All the nano sheets have been solved by one of my students, Paul. He has done the whole thing. And most of the nano sheets, he has given answer. And all these papers are already published. So you can have a look at these papers also. But then architectures like butterfly, Banner's network, telecommunication, that is the circular networks, they have not been solved so far. So look for literature survey. I do not know, even today some paper might have been published. So look for literature survey, and then you start working on these problems. Okay, now I'm quickly going to go through the next one because I have some problem with my network. So I may not be able to spend more time. So transmission in networks is next problem, which is a very interesting problem. What is transmission? Again, passing on data from one to the other. Let us see how it does. So I need a concept called edge cut. What is an edge cut? When I remove, the graph falls into 2 pieces. Okay, that is more called the edge cut. So these edge cuts, we study what are the edge cuts, why they are used, how they are used, to solve what problem. So Wiener index problem can be solved, embedding problem can be solved, transmission can be solved, closeness centrality can be solved. All right. So you know what is a edge cut. Now what is a convex set? Convex set means take a graph, take the vertices marked in red. That is a subgraph. Now, if I take any 2 vertices in this subgraph, note the word every shortest path between 2 vertices lies wholly in that particular set. Okay, so that is called a convex set. Okay, so let's have some more example. Let us look at the mesh. A, B, C, D is a subgraph. Okay, and all the edges between A and the next one, the horizontal edges, if I cut, then I get 2 components. I find that if I take any 2 vertices Please look at only the left-hand side. If I take any two vertices A and C, there is only one shortest path that lies only in that particular component. Whereas on the right-hand side, there is a line drawn, that is a cut. What is the meaning of that line drawn over there? All those edges are removed. When all those edges are removed, the graph falls into two components. When it falls into two components, you find that this components, they are not convex. Can you tell me why? Take D and F. D, E, F lies in one component, but there is one more. Travel horizontally to the left and come down to F. That does not lie in that particular component. So every shortest path should lie within that component fails. Therefore, this cut is not a convex cut. All right. So convex set, convex cut. So what is it? Now let us look at another example. Look at this particular cut. Is it a convex cut? Let us look at it. Remove the vertices. You find that there are two components. Given any two vertices, all the shortest paths lie within that. Therefore, they are convex sets. Now let us look at one more. The same graph. I am giving another cut. When I remove those edges, I find that I get two components. Now look at the answer. Look at V2 and V4. V2 and V4, you have V2, V3 and V4 lying in that component. But V2, V1 and V4 is another shortest path which does not lie in that component. Therefore, this cut is not a convex cut. Okay. So all these are examples of convex sets, convex cuts. Now let us look at the next one. Convex partition. What is a partition? Take the edge set, take all the edges, and now in topology you would have studied, real analysis you would have studied. Partition means a collection is said to be a partition of a set if none of them is empty. Sujata ma'am.
Yes, ma'am.
Can you give me 2 minutes?
Yes, ma'am. Yes, ma'am.
Mama, please. We are having a severe problem here. I didn't expect this. Give me 2-3 minutes time.
Ma'am, no
Pardon me?
problem, ma'am. No problem, ma'am. We will wait, ma'am.
Yeah, just 2 minutes, 2-3 minutes.
Participants, ma'am will join. Please cooperate.
Am I audible?
Yes, ma'am.
Okay. Is it visible?
Ma'am.
Okay.
Yes, ma'am.
Okay. All right. So we spoke about the convex set, convex cut, and the convex partition. Now we have to talk about convex partition. What is this convex edge partition? Take the mesh. You find S1, S2, S3, S4. They are all edge sets. Okay. So the S1 is all the three vertical edges. S2 is another three vertical edges in the bottom row. So if you take these sets S1, S2, S3, S4, they form a convex partition. Partition means union should be all the edges in the graph. So you have the partition means none of them is empty. They are pairwise disjoint. Union will be equal to the set of all edges in the graph G. Okay, so let us now go to the problem. What is meant by transmission of a vertex? Take a graph G, take a vertex in that graph. Transmission is defined as the sum of all distances from that vertex U to every other vertex in the graph. I repeat, the sum of distances from that vertex U to every other vertex in the graph. So if you find, sorry, so you take this U, you find that the distance that 2 is the distance of that vertex from U. Then it is 1. Then take the rest of them. When you take the sum, the answer is equal to 32. So according to my definition, the transmission of U is 32. All right. Now, the question is there an algorithm that will calculate sum of distances without calculating the distance? Why this question arises? Let us look at this particular one. How many units of time did you spend to calculate this? There are 16 vertices. One of them is U, of course. There are other 15 vertices are there. So the time spent to calculate this is 15 units of time. Whereas, if you want to avoid this, if you want to bring down the time, what shall we do? So that is where we use our convex partition. Let us look at S1. Look at S1. Remove all the edges which belong to S1. So you get two components, G1 and G2. In these two components, what we notice is there is one component which does not contain U, the other one which contains U. So I take that component which does not contain U, find out the number of vertices in that component. So in G1, there are 4 vertices. All right. Now, I do this for every cut. So S1, you have 4. When I come to S2, I have 8 vertices in the component which does not contain U. Similarly, if I go to the next one, I get the number as 4. This goes on till I cover all the edges. Now, how many units of time have I spent to find this out? Here you find there are 6 cuts. So I have spent 6 units of time to find this answer. So to find out the same transmission, you spent 15 units of time. Now it is only 6 units of time. What will happen if you have a 10 cross 10 matrix? If you have that, then there will be 9 plus 9, 18 units. So in 18 units of time, you will be able to get the answer. All right. So then time is reduced drastically to find transmission of a vertex. All right. So finally, you get the answer as 32. Try this for a tree. V is the vertex marked in red. And let us take the first one, that 8. What is the meaning of 8? Remove that edge. There are 2 components, one which contains V, the other which does not contain V. The component which does not contain V, how many vertices are there? There are 8 vertices, and therefore that number is 8. Can you tell me what is the reason behind having that as 8? The reason is when you travel from V to 8 other vertices on the other side, you travel through that particular edge which is removed 8 times. So instead of calculating the length of that path, you are now calculating what is called congestion. What is congestion? Number of times you cross a particular edge. 8 times you crossed, 6 times you crossed, once you crossed. So it depends on how many times you crossed. And for example, suppose you take the vertex which is straight down below V. What is the length of that path? Length of the path is 1 to travel from V to that vertex. Now, you are traveling that edge once. Suppose you take the next vertex which is adjacent to the edge marked 8. Again, from V to 8, to that vertex, it is only 1. But then there are 8 other vertices on the other component. So you will be traveling that particular edge 8 times. That is the reason why you write 8 there. This is the theory behind why we write all this. So instead of calculating the entire length, you are calculating the congestion. Congestion means number of times you cross a particular edge. Okay, that result that we discussed just now is translated into a lemma called transmission lemma. This transmission lemma can be used for any architecture, and we have actually published many more results using this particular lemma. Sometimes what happens is two transmission lemma. What is this? Sometimes we will not be able to cut the edges exactly once. Partition means exactly once. Sometimes it is not possible. There are architectures where it is not possible. So what happens with such architectures? Let us take this triangular grid. Take this cut. So you find out all the edges which are cut by this and find out that component which does not contain you. Remember that the two components are convex. What is convex? Every shortest path between any 2 points will lie in that particular component. Okay, so now you find 6, then you find 10, then you have 6, 4, 3. All right, now what happens is, note this, this is not a partition. What is a partition? Every edge has to be cut. You find that topmost rectangle, left hand side edge is not cut yet. So I'm going to cut it once again. Let us see how it is cut. I find that the other two edges are cut. When I do this, I do the same calculation. But unfortunately, what has happened? Some edges are cut twice, some edges are cut once. So to make it uniform, I go for another set of cut edges. I cut like this and find out the total sum. The total sum is 88. And because you have cut it 2 times, every edge is cut. Just check, every edge is cut 2 times. Therefore, you have to divide by 2 because the congestion on each of the edges is taken twice. Therefore, the transmission, you have to take half of that. Okay, so there are several architectures where 2 cuts are necessary. What I'll do is I'll take the sum and divide by 2. Suppose so far we have not found architectures where every edge is cut 3 times. We have not done so far. We have not found so far. If you are able to do that, take the sum, divide by 3, you will get the transmission. All right. So those problems are still open to us. Now, finally, this is the last one. What is meant by closeness of a vertex? reciprocal of transmission is called closeness of a vertex. Many centrality measures are there. This is one centrality measure which is called closeness. Why is closeness study? You should know how close a node is to all other nodes in the network. It is centrality measure. All right. So these are all the questions that we'll be answering if we study closeness. To study closeness, what is that we have to study? We have to study the transmission of vertices in a graph. How influential is a person in a social network? So these are all some of the questions that we will be able to answer if you know closeness, which lead to transmission. Transmission leads to your convex cuts, convex partition, and these are and edge cuts. These are all grouped under one classification where you can solve several other new problems. So nano sheets, you should know how to cut. This is one such cut. Then there is another problem which is introduced in the year 2014. Same problem. Do the transmission for each one of these vertices. Find out how many distinct distances are there. 32 is there, 40 is there, 48 is there. So you find that this dimension is equal to 3. Here again, here is an open problem which has not been dealt with by many people. All right, many people have not done what is dimension, transmission dimension. For mesh, it has been worked out, but several other architectures still remain open. Therefore, you can go for transmission distances and find the transmission dimension. Another illustration is you take this particular tree. Okay, now you find the distances, the transmission distance for each one of the vertices. 25 means that particular vertex, the sum of the distance from that vertex to every other vertex is 25. 19 means sum of distances from that vertex to every other vertex is 19. Now, if you keep doing the distances, it takes a lot of time. That is why we have used the cut method. This cut method gives you, in no time, you can calculate the transmission of vertices. Here you find there are 5 distinct numbers: 25, 19, 17, 19, and 33. There are 5 distinct numbers. Therefore, the dimension is equal to 5. And the last one is the Wiener index, which many of you would have studied. Wiener index means sum of all the shortest paths between all pairs of points. Sum of distances between, shortest distances between all pairs of points. Because you are calculating from both ends, we take 1 by 2. All right, Wiener index is studied 64 times. I calculate, add them up and find the Wiener index. But if you use cut method, what is that? There are 3 cuts that I'm going to talk about. Look at the cuts: 1, 5, 3, 7, 2, 6, and 4, 8. Look at the diagram there: 1, 5, 3, 7, 2, 6, and 4, 8. If I remove that, the graph falls into 2 pieces. All right, 2 components. The 2 components contain how many edges, how many vertices? 4 on one side, 4 on the other side. For a transmission from a particular vertex, from here, it is from all vertices. Therefore, 4 into 4 will be the congestion on that particular S1. Let us go to S2. S2 is remove the edges 1, 3, 2, 4, 5, 7, and 6, 8. Again, the graph falls into 2 pieces, 2 components, each containing 4 vertices. Therefore, the number of crossings will be 4 into 4, which is 16. Do the same thing for S3. You find that this is a convex edge partition. And finally, if I add up all that, it is 42. I think it is 42. And that gives the Wiener index of this particular graph. So in how many calculations did you work it out? In 3 calculations. In 3 units of time, you could get this answer. Therefore, the time is brought down. So you find that Wiener index, transmission, all these problems can be used using edge cuts. All right, these are some of the open problems which we have not tackled so far. To my knowledge, these have not been solved so far. But as I told you in the beginning, your first thing that you have in research is you should go for literature survey. All right, And sometimes it happens, even after all that, you will find that somebody else would have published your result already. Not your result, they would have done it independently. Don't lose hope. That means you are proceeding in the right direction. Go to the next problem and then start solving the same problem. You keep working on the same problem, you will definitely find you are getting better and better results. Okay, these are references for Wiener index and transmission. And now what we have discussed is few problems. There are thousands and thousands of problems in graph theory. Few problems we have done. It is a voyage. We keep exploring again and again. And this is the secret of research. What we do is we keep digging. When we keep digging, suppose I am working on burning number problem, I don't get a result. Then after 1 month, I say this is not good. I go to the next problem. I start with transmission. I start digging there. I don't find water there also. The reason being, you don't concentrate much on that particular problem. You keep working on it. It may take some time, but once you start finding the results, definitely you will find water. And if you keep on digging, you will find water. And definitely one particular stage, you will be an expert in writing a number of papers that can be published in very good journals. Okay, thank you. And I'm sorry, in between there were a lot of disturbances. I take up the responsibility. It was due to some problem in my place. Thank you.
Thank you, ma'am.
Okay, ma.
Thank you, ma'am. Your presentation drew the audience in and held their attention. The session was informative. Now, Mr. Navin sir, Assistant Professor from Little Flower Degrees College, will take over the question session. Participants, kindly post your question in the chat box or you can raise your hand. Over to Mr. Navin sir.
Thank you, Nandini. I request all the participants, if anyone has a queries, please, you can raise your hands or else just post your queries in the chat box so that the madam can answer one by one. So there is one query from the chat box, ma'am. One participant has asked that what sort of applications we can give in the graph labeling.
Okay. Graph labeling is partly associated with coloring. If you are interested in labeling, then try to read papers on lucky labeling. Okay, I don't have the reference here. Probably if you are interested, you can write to me, I can give you. Lucky labeling, what it does is it gives a label. It's like any other labeling, harmonious labeling or graceful labeling or anything. Lucky labeling says you label the vertices and add up all the adjacent vertices to that particular vertex. Okay, the label of that vertex, and that will be the end result that for that particular vertex. Do that for every vertex. Finally, apply coloring concept to it. You will find that the coloring problem can be solved via labeling. So coloring has got a lot of applications. So this lucky labeling, there are several lucky labelings. Sigma coloring, please note down, there are two things. One is lucky labeling, the other is sigma coloring from Chartrand. Chartrand has given sigma coloring. Lucky labeling is one which is giving coloring problem. So if you read these two papers, you'll find a lot of applications in labeling.
Okay, thank you very much, ma'am. Ma'am, one more question.
Yeah.
Can we apply this linear algebra concepts in the graph theory, ma'am? That is how to find the characteristic of values and the pivot column. Already we have that non-pivot columns and pivot columns. Can we apply these concepts in the graph theory, ma'am? Which
Yeah,
can be
see the
related
energy.
to...
No, that is that part of it I'm not very good at. But we have what is called the energy of a graph. No, the matrix associated with that particular adjacency matrix. This one, incidence matrix. These are several matrices associated with a graph, and definitely matrices are associated with linear algebra. Okay, so if you want to solve a particular problem there, probably you have to explore this. Okay, so probably you can convert it into a matrix problem. That matrix problem can be thought of as a graph theory problem. So as a sequence, sequentially can this be done? Energy of a graph is done already. Cayley graphs are there, which associate algebra with this, but not linear algebra. But linear algebra means definitely it is with the matrices.
Matrices. Thank you, ma'am. Ma'am, one more small doubt, ma'am. In
Yeah.
this session, you have gone through the so many number of problems, ma'am. That is
Yeah.
locating, dominating problems and burning model problems, in
Yeah.
which you have used only the graphs. That is, you have used only undirected graphs. Can we
Yeah.
proceed to directed graphs also, ma'am?
Yeah,
These
you have
methods,
to
whatever the methods.
method will have to be redefined. Okay,
Yeah.
the method, suppose I say cut method, one edge will be crossing upward, another will come down, or maybe in the opposite direction, in which case I have to redefine my cut, which has not been
Yes,
done so far as far as I see. Methods, I'm talking
For
about
direct,
methods, I'm not talking
yes,
about
ma'am.
directed ones. Yeah.
Okay. If suppose the graphs are directed, ma'am, if they have
Yeah.
the direction here, then can we go with this methods? Like,
No, the same method cannot be applied.
okay, we need to
Because
change
you just see transmission from a vertex means distance of that vertex to every other vertex. Once you specify a distance, a direction, it may not allow you to proceed immediately. Okay, you may have to go in a roundabout way to go to that particular to other vertices. Do you understand? Strongly connected says every pair of vertices will be connected by some directed path. That is fine. So probably you will take strongly connected, but there is no guarantee minimum number of edges will be used. I think we can very well imagine, because the direction may take you to any place and come back to that particular point. Okay, so the methods will have to be redefined. Probably we'll have to think that these are all areas. If you keep on thinking, one day you will find some answer there.
Yeah, one more small
Okay.
doubt, ma'am.
Yeah.
Actually,
Yeah.
in a burning method problem, you said that number of vertices. Actually, do you have any limit for this one, for a graph, that the number of vertices should be a finite?
No, these are all
that is a
dealt.
particular thing.
These are all dealt with for finite graphs only. Finite can be a million vertices. Okay, that is different.
Okay.
Facebook is a finite graph. Okay,
Okay.
you may have millions of vertices there, but it is a finite graph. Okay, so what all we have suggested here, they are all, whether it is small or big, they are all for finite vertices. But then the burning number, the concept can be extended to infinite. Infinite in the sense you keep on adding. You can at any point of time you can add vertices to that. Okay, so that part of it has not been covered here.
Okay, ma'am. Ma'am, one more
Okay.
small question from our participants, ma'am.
Yeah.
If you compare the results of directed graph and indirected graph, which results will be an accurate results?
No, it all depends on the problem. No, see, there is a problem called oriented diameter. Diameter of a graph means the maximum distance between pairs of vertices. When it becomes directed graph, that direction will take you to some route, some path. It may get extended, so that diameter may be very long. Okay, so for me, for a network problem, my diameter should be short, should be as small as possible. Why? Because I have to communicate my data from one end to the other. If it is going to take a longer route like this, I may not like it. But then in multiprocessing, what is multiprocessing? Several processing will take place at the same instance. So the same line, same path cannot be used to travel from vertex number 1 to vertex number 2 and from vertex number 2 to vertex number 1, in which case you definitely need a directed graph. So when there is a necessity, you cannot throw it away. You have to go for directed graphs.
Okay.
Even though the time may be more, the diameter may be more, but still, if the problem necessitates that you should go for directed graphs, and mostly from computer science point of view, they are all directed graphs. Most of them are directed graphs.
Okay, ma'am. Thank you very much, ma'am. Participants, do you have any questions here? Please, if you have any questions, you can just raise your hands, or else you can just unmute and you can ask. Yes, anyone?
Ma'am, is there a real-time application for burning number point, ma'am?
Yes, ma. That is why that problem is taken up. See, I told you, no, COVID situation or any outburst of some epidemic or pandemic. See how fast it is going to spread. You should know, no, as a see, as a social worker or a doctor, you should know how it is going to spread. So if there is a protocol, if this is going to burn all the neighbors, if it is going to spread to all the neighbors, how far it is going to how fast, sorry, how fast, okay, it's going to spread. That is one way of looking at it. Another way of looking at is, you have a data with you, I want to send it to uh, every member of the network. What my protocol is, I will whisper or send that data to all my neighbors, but then I cannot simply stop. There is a propagation protocol. This protocol says, okay, I will choose one more fellow where I will give the data, so I will feed the data. So in minimum number of places I must feed the data, so that the entire network gets the data. Okay, these are all some of the practical
Thank you, ma'am.
applications. Okay, ma.
Yes. Thank you, ma'am.
So,
Yeah.
any of the
Thank you.
questions from the participants? I think I don't find any kind of questions from the participants. Thank you very much, ma'am, for giving a lot of information about the graph theory. Because
Thank
actually,
you.
when we just studied about the higher studies here, graph theory means only directed and undirected graph, and some we have Hamilton like matrices also. But
Yeah,
today
yeah,
we have seen a lot of different models actually, the locating, dominating graphs, and especially the burning number. We have
yeah,
seen a lot of new concepts actually in the graph theory. So
yeah.
it was very informative, ma'am. It was very informative, and even I hope the participants also got a lot of information regarding this research. Thank
Thank
you very
you.
much, ma'am.
Thank you.
Over to Sujata, ma'am.
Yes, sir.
Thank you, ma'am, and
So
thank you,
Nandini
sir.
can start.
Now, Ms. Aruna and Ms. Priya, assistant professors from Auxilium College, will present a brief report on a 5-day national level online PDP.
Good evening to one and all present here. It's my pleasure to give a brief report of a 5-day national level online PTP on writing research articles in mathematics and statistics, jointly organized by Little Flower Degree College, Hyderabad, Telangana, and Auxilium College, Autonomous, Velo, Tamil Nadu, from 26/9/2022 to 30/9/2022. The organizing committee members are Reverend Brother Vincent Reddy, Principal and Correspondent, LFTC, Reverend Sister Alice Katie, Secretary, Auxilium College, Dr. Sister Jayshanti R., Auxilium College, Mrs. P. Jayanti Reddy, Vice Principal, LFTC, Sister Sumati M., Dr. Sister Amala Valarpati A., Vice Principals, Shift 1 and 2, Auxilium College. The head and staff members, Department of Mathematics, LFDC, and Auxilium College. Over to Ms. Priya.
Was held on September 26. The research person was Dr. Sundarram, designation HOD Department of Mathematics, Chaitanya, deemed to be University, Varangal. இல்ல, சொல்லிட்டு இருக்கேன்.
The day one section was held on September 26th. The resource person was Dr. Sundaram, HOD, Department of Mathematics, Chaitanya, Dean to be University, Varankal, Telangana. The talk on the topic was Fluid Dynamics for Researchers. Sir started the section by giving the difference between the pure mathematics and applied mathematics by giving various examples. Sir focused on the main areas such as fluid dynamics, mathematical modeling, operations research, simultaneous based computational technique, which gives a lot of scope in the field of mathematics. And also, Sir gave brief description on objectives of operation research, and also he explained about fluid dynamics by analyzing them with a live example which defines hydrodynamics, hydraulic, gas has a third having a study of basic law of physics, which says more about the properties of fluid density functions involving pressures, temperatures, and so on. In this section, Sir has also added different mathematical models for different fluid flows. Some of them include Cashian fluid flow, Jeffrey fluid flow, Maxwell fluid model, etc. The concluding part consists of different boundary conditions which should be involved in the analysis and taken into consideration for finding the solution. The day two section was held on. September 27. The resource persons was Dr. Samalti, University of Swayam Coordinator, Assistant Professor, Department of Paramedical Science, HNP, Garhwal University, Srinagar, Garhwal, Uttarakhand. The talk on the topic was Nuances of Research Article Writing. Sir has focused on the drafting a manuscript, which are essential aspects in the area of research. Sir started the section with the 9 characters of Guru, which gave us a strong determination to do things in a positive way. This process involves critical thinking, first draft, multi-draft, etc. He explained the basic traits of writing the research papers. He targeted the journal which enable the research scholar with good scope in the research field, especially with good H index. Sir focused on the IMRAD, which elaborates the detailed information about the necessary requirements of the research article. Sir also discussed about the basic aspects of writing the writing skills, and he focused on every component of it, which plays a vital role in writing the journal, and also added that the concluding part of the journal should be specific and concise with the English, which is simple with lots of information. Now,
The day 3 session held on 28/9/2022. The resource person of the day was Dr. Indrani Pramod Kilkar, subject admin, engineering and science, Tata Consultancy Services, TCION, Hyderabad. She gave a lecture on the topic mathematical modeling for researchers. Ma'am has given deep insights of mathematical modeling and its type with lot of real-world examples. She gave clear explanations on how real-world problems are classified into black box models and white model with numerous examples. We have learned characteristics of good mathematical modeling with real-world situations. She explained the classifications of models on how different categories and characteristics of good mathematical modeling. We have also learned the steps involved in mathematical modeling, which includes formulation, finding the solution, interpretation of the solution, and checking the good representation of the problem with appropriate results. The concluding part of the session consists of designing aircraft using mathematical modeling. The day 4 session held on 29/9/2022. The resource person of the day was Professor V. Hara Gopal, Professor, Department of Statistics, Osmania University, Hyderabad, Telangana. He gave a lecture on the topic Applications of Regression in Stochastic Model. Sir has given clear explanation on simple linear regression and multiple linear regression, and we have learned more about the usage of SPSS software for computing the hypothesis testing and to find out the best fit. He explained about the different types of data collection and types of regression with medical examples in statistics. He demonstrated the plotting, the scatter diagram using IBM SPSS software. He gave deep insights about stochastic process, probability distribution of the process, followed by covariance and autocovariance of the stochastic process. In the concluding part, Sir has given deep explanation on different stochastic modeling with suitable case study. Over to Ms. Priya.
The day 5 session was held on September 30. The resource person was Dr. Indra Rajasingh, Adjunct Professor of Mathematics, Savita School of Engineering, Chennai. She gave a talk on the topic Research Problems in Graph Theory. Ma'am started the session with the basic definitions of graphs, and how the verticals and edges connected with the real situation. She gave a detailed explanations on interconnection network, butterfly network, circular network, and its different types. She taught how dominant is helpful in monitoring communication network and electrical network. Ma'am explained the importance of LDS and the working model with a real life situation. Ma'am gave valuable tips for the researchers, particularly literature survey and research papers from high impact factor journal. She inspired us with a way of connecting each definitions with a real life situation. It makes us easy to understand the concept thoroughly, ma'am. Ma'am gave the importance of optimization and explained about the coloring, chromatic number, edge chromatic, acyclic chromatic number. And she discussed many open problems in graph theory at the final section of the part. Thank you.
Thank you, Ms. Aruna and Ms. Priya ma'am. Hope a 5-day national level online PDP has equipped the faculty members with skills and knowledge in writing research articles in mathematics and statistics. I now request a few participants to give us your feedback.
So, dear participants, you can share your views regarding about the program that is PDP. Any participants?
Good evening to one and all gathered here. I am Alina Julie Mariam Anton from Auxilium College. First of all, I thank all the coordinating committee for organizing this 5 days online PDP, which enlightened and provoked in me the application of mathematics and many ideas that would lead me into a research scholar. I have also gained more knowledge on the following topics such as fluid dynamics for researchers, article writing, mathematical modeling, applications of regression and graph theory. Hence, I thank all the resource persons who have rendered their splendid time for the welfare of the students community. Thank you.
Yeah. So thank you everyone. So from both the institutions, that is from Little Degree College and as well as the Auxilium College, I thank all the resource persons for accepting this invitation for this 5-day national PDP program and giving their valuable information by spending their precious and valuable time and giving a lot of information on various topics by analyzing them and showing them to all the participants. And even I thank all the participants right from the first day onwards here, first day to fifth day, those who have come and joined and spend their time in giving their valuable feedback to us. So thank you one and all. And I thank each and everyone, those who have supported this program to make this one as grand success. Thank you. Thank you one and all. So feedback link, today's feedback link is posted in the chat box. You can please start filling that. So this will be enabled till the session continues. As soon as the session closes, that will be disabled. So I request all the participants to please fill the feedback form as early as possible.
Thank you, participants, and thank you, staff members, for their feedback. For your feedback. Feeling gratitude and not expressing it is like wrapping a present and not giving it. To express our gratitude, I now invite Dr. Sujata, Assistant Professor and Head, PG and Research Department of Mathematics, to propose the vote of thanks, followed by National Anthem.
Every story has an end, but in life, every end is just a new beginning. Good evening, all. Thank you is such a prayer that cannot be seen or touched. It must be felt by the heart. I feel honored and privileged to propose the vote of thanks on the last day of a 5-day national level online PDP on writing research articles in mathematics and statistics, jointly organized by the Department of Mathematics, Little Flower Degree College, Hyderabad, Telangana, and the PG and Research Department of Mathematics, Auxilium College, Autonomous, Vellore, Tamil Nadu, from 26 September to 30th September 2022. First and foremost, I thank Almighty God for blessing us abundantly for the smooth conduct of this 5 days national level professional development program through virtual mode. I convey my deepest gratitude to all the resource persons from day 1 to day 5, namely Dr. Sundar Ram, Head, Department of Mathematics, Chaitanya deemed to be a university, Warangal, Telangana. Dr. Ajay Seemalti, University Swayam Coordinator, Assistant Professor, Department of Pharmaceutical Sciences, HNB, Garhwal University, Srinagar, Garhwal, Uttarakhand. Dr. Indrani Pramod Kelkar, Subject Admin, Engineering and Science, Tata Consultancy Services, TCS Ion, Hyderabad. Professor V.V. Haragopal, Professor from the Department of Statistics, Osmania University, Hyderabad, Telangana. Dr. Indra Rajasingh, Adjunct Professor of Mathematics, Savita School of Engineering, Chennai, for the most interesting, inspiring, and informative resource talks. Never stop learning, because life never stops teaching. No event can happen without the provision of a vast network of people. We are very happy to see the huge response to this program. On behalf of Little Flower Degree College and Auxilium College, I express my gratitude to all the faculty members and research scholars without whom this program will be incomplete. Also, we are very happy to receive the positive feedback from your side. An event of this dimension cannot happen overnight. It required meticulous planning and execution. The successful culmination of this program goes to the organizing committee members. Their unflagging energy and dedication made them organize this academic program systematically. I express my heartfelt gratitude to Reverend Brother Vincent Reddy, correspondent and principal, Little Flower Degree College. Reverend Sister Alice Katie, Secretary, Auxilium College. Dr. Sister Jayashanti, Principal, Auxilium College, for their motivational words and constant support. My deepest sense of thanks to Mrs. P. Jayanti Reddy, Vice Principal, Little Flower Degree College, Sister Sumati and Dr. Sister Amala Valarmadi, Vice Principals of Shift 1 and Shift 2 Auxilium College, for their wholehearted support and guidance. We have been fortunate enough to be backed by a team of very motivated and dedicated colleagues. I express my most sincere appreciation to the head and faculty members of the Department of Mathematics, Little Flower Degree College and Auxilium College for the involvement they have shown and the willingness they have expressed to take on the completion of tasks beyond their comfort zone. Thank you, one and all. Happy learning.
Thank you, ma'am.
Thank you very much, ma'am. Sujata, ma'am.
Thank you, sir.
Thank you, ma'am.
Thank you very much, ma'am. Yeah, so I request all the participants to please fill the feedback form, which is posted in the chat box. And that will be disabled as soon as the session closes. So after filling the feedback form, you can please leave the session.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
The ma'am is there in the meeting. The ma'am is there in the meeting. Ma'am,
Yes,
thank you
ma'am.
so much, ma'am. Thank you so
Really,
much
thank
for
you very much.
accepting our
Thank you.
invitation.
Ma'am. Thank you very much.
I request the participants to switch on the video so we can take a photo along with the resource person.
Yes, I request all the participants to please enable your camera so that we can have a screenshot with our resource person. Yeah, thank you very much. Thank you, everyone.
Thank you.
Thank you, ma'am.
Thank you, ma'am. Even though you face a lot of problems, you have conveyed everything to the participants, ma'am. Thank you so much.
I really felt very bad, ma'am. First time this has
No,
happened.
no, ma'am.
Okay,
No,
ma'am.
ma'am.
Thank you.
Thank you
Anyway,
so much. ma'am.
anyway, you were all patient.
Thank you so much, ma'am.
Okay, I'll leave.
Okay,
now.
ma'am. Yes, ma'am. Yes,
Yes,
ma'am.
ma'am.
Okay.
Yes.
So I thank Prashant sir, Naveen sir.
Yeah, ma'am.
Thank you.
Meena,
Also,
ma'am.
thank you. Thank you very much, ma'am. With your coordination and support, we could just complete this program.
Because of this
Otherwise,
5 days.
yeah. So
So everything
I
went on
request-
well. Thank you so much, ma'am.
thank you very much, ma'am. So please fill the feedback form. We'll give you a time of 15 minutes. Please, all the participants, those who are there in the session, can fill the form, which will be disabled after the session closes.